We're going to start with an invite talk by Nathan Jacobs. And then, as I mentioned in the morning, one of our co-organizers and friends, Aki Kotori, sadly passed away at the beginning of the year. And Tomasz, Josef, and I will talk a bit about Aki and his work. Then we're going to have an invite talk by Angela Dai from TU Munich, and we'll wrap up with one talk on the visual localization challenges. Again, thanks to our sponsors, Microsoft, Naval Labs Europe, and Niantic, for sponsoring this workshop. And if you want to know more, please visit the workshop website. And with that, we are through with the introduction. And it's my pleasure to welcome the first invited speaker, Nathan Jacobs. Nathan got his PhD in computer science at the Washington University in St. Louis in 2010. And since then has been a professor of computer science at the University of Kentucky. He's working in computer vision with a specialty in developing learning-based algorithms and systems for processing large-scale image collections. His work currently focuses on developing techniques for mining information about people and the natural world from geotagged imagery, including images from social networks, publicly available outdoor webcams, and satellites. His research has been funded by NSF, NIH, DARPA, YARPA, NGA, ARL, AFRL, and Google. And I'm very much looking forward to his talk.
Okay, great. Is that all showing up nicely?
Yep, I can see everything. Great. Thanks.
Okay, great. So today I'd like to give a talk. The title I'm working with is Exploring the Intersection of Localization, Mapping, and Image Understanding. And I know this workshop is more focused on the localization aspects, but I thought I would sort of explore the sort of related problems a little bit. And so, if we look in the, I tend to think of, computer vision problems related to localization like this. There's sort of three related problems. One is the localization and calibration problem, which we have in the upper left. And if we think about that probabilistically, we can think of that as just estimating a probability distribution over location and pose from a given image. Related to that is the problem of image understanding, where in particular we'll focus on the idea that it's a probability distribution over some aspect of appearance given an image, and this is closely related to this problem of appearance mapping. So the idea there is you want to estimate some distribution over appearance given location, pose, potentially other variables. And so what I'd like to argue is that these problems are very closely related. And so I want to dig in just at that sort of conceptual level first before talking about some specific ideas. So if we think about the localization problem, and we start with the idea that we have two things already at hand. We already have some appearance mapping. So we already know the relationship between appearance and how that depends on location and pose. And we have some ability to extract appearance features from an image. Then we can use that to build a system for localization and calibration, right? So essentially you could extract image appearance from the image you want to localize and relate that to some map that you have that describes where given appearances are likely to occur, right? And so this sort of shows that these two problems of image understanding and appearance drive and lead towards localization and calibration problems. So I'm not going to dig into examples of this. We've seen lots of examples of this in the context of this workshop and other papers at ECCV. We can also look at a slightly different version of this, where suppose that we have localization and calibration. That problem is solved. And so we know for a given image, its location, its pose. We might have some uncertainty in that. We might have been handed that because the person took a picture and it told you the location and pose. But suppose that we have that, and then suppose that we have some map of appearance given location and pose. And this could be all sorts of different things, but suppose that we have that, we could use that to train a system to do image understanding, right? So we can essentially say, we know where this image is located. Now let's look at the appearance that we expect, and now we can try to predict that appearance and train a model to do that. A good example of this, this is an interesting paper from WACV 2015, essentially explores this idea of taking geotagged, geolocated images, and then GIS databases that tell you what the population is, what's the GDP, what's the elevation, and uses that to train a system to do image understanding. Right? So we've taken location information, pose information, and an appearance map, and turned that into a system that can do image understanding. And the thing that I want to talk about a little bit more in the context of this talk is this third alternative, which is the idea of taking something that does location and calibration, something that does image understanding, and using that to build a map of appearance. So if I can take any ground level image and I can tell you where it's located, and I can extract appearance features, then I can use those as samples of some broader distribution that captures the relationship between location and pose and appearance. Right, and so this is broadly appearance mapping, and people will do this at many different scales, from the very local scale to the broader scale, which is generally what I focus more on. But a good example of this is this very, very cool ECCV paper called Crowd Sampling the Planoptic Function, essentially taking a collection of consumer photographs, running an SFM, building an SFM model, and then showing how you can use that to extract a model that describes the appearance of individual pixels and how that relates to time. And so in a sense, a very highly localized, fine-grained appearance map. And so what, this is sort of one way of starting, where you start from a highly localized, very specific model. And the work that my group has been doing is looking more at this from a global perspective. So, sort of implicit in a model such as this is the relationship between the appearance and geographic location and time. Right? And so that's what we've been looking at. And I thought I would describe 3 examples of work that we've been doing in this area. So one is on mapping scene classification, one is on mapping objects and their distributions, and then more recent work focused on dynamic appearance mapping. Right, so we start from this idea that we have, a large repository of geographic locations tied to images, right? And so these become samples of the appearance distribution that we can work with, right? And so the basic idea for these 3 papers sort of starts from this crude diagram that I'll show first, right? So the idea is that we're going to take some existing CNN, right? And so this is the image understanding part of that 3-part figure that I showed before. So we have location information, we have image understanding, and now we're going to treat those as a collection of weak labels to learn how to do appearance mapping. Right, and so this is a fairly standard thing that we might do, is take geographic location, find the satellite imagery of that geographic location, and now that's an overhead view of this ground level image here. And now what we're going to do is train a new neural network that predicts the labels that we extracted from our existing ground level image understanding system. Right, and what's, in my opinion, really cool about this approach is that the advance of neural networks for understanding ground level images has made it so that we can essentially trust those to serve as a really strong, while still weak and still noisy, but fairly good labels for training something to understand satellite imagery. If these features that we're extracting from the ground level image are related to their appearance, which they almost certainly are, then essentially what we're learning is to map visual appearance with this basic process. And we don't have to collect any new labels, explicitly annotate anything. We just use the ability to collect large numbers of geotagged images and the availability of image understanding neural networks. So the first example of this, we refine this general idea of appearance mapping to the specific task of estimating what the distribution over scene categories is for a given geographic location. And to support this, we built a large data set called CVUSA that relates ground level images with their corresponding overhead images. And so we have images in this data set from Google Street View and from Flickr, around 1.5 million total ground level images with a variety of different satellite images to go along with those. And so we start from this, we have a collection of pairs of ground level and overhead images. From the ground level images, we extract the scene category using some off-the-shelf neural network. From the satellite image, we essentially try to predict the scene category from the ground level image. And then what we have out of that is a neural network that takes satellite imagery and tells us the type of scene we would expect to see if we were to take a picture on the ground at that location. And from that, we can make maps of scene categories and do quite a few different things. We've shown how we can use this for ground level image localization. But I thought I would just show one of the pictures that comes out of this model. So the idea here is that we might take this ground level image here at the left, extract the scene categories for that, and then just look at the KL divergence between the scene category distribution that we get and the predicted distribution for a given geographic location. And then we can essentially make heat maps of where we expect to see a particular scene category that is seen in this image. Right, so we can see where highways are in the United States. We can see where places are that that are lakes, and we can see more desert regions. And so this is one of these things that sort of falls out, and you could see how this might be useful for localization because it puts a strong prior over places where this ground level image is likely to have been taken. The next piece that I'd like to talk about is on mapping object distributions. So the idea here is similar. We're going to refine this and think about the distribution of objects for a given location. And so the idea here is that we take our CVUSA ground level images that were from Flickr. We run an off-the-shelf object detector on this, which gives us, for every image, a collection of objects, which then are related to the satellite image of that given location, right? And so now when we think about, what we might want to extract from a satellite image, we often think about things like land use and land cover. And in some way, this is a proxy for those tasks, except it's, it's not something that's quite so nebulously defined as land use and land cover. It's actually, where we would be thinking about what are the objects that are likely to occur in a given location. Right? And so that's essentially what we want to get at is that question. And so we can take our images, we can build a histogram over the counts of the different objects that were detected. And then what we could do is, if we ignore the satellite imagery for a moment and just think about making a map that tells us how many objects of a particular type we would expect to see in a given location. And so this picture here at the left is a heat map that essentially shows where, if you were to get a picture from that location, how many boats would be in that image. And so you can see, if you know much about the geography of the United States, places where there are recreational lakes that people use. You can see, I believe this is Lake Powell here. You can see the large amount of boat traffic in Lake Michigan. Also similarly here for the distribution over trains. So if you know much about the United States, Chicago is a major rail hub, and there are trains that propagate out from there heading west. And so you can see evidence of those lines in this model. But this is just looking at the ground level images and trying to make a map out of that. And it doesn't actually capture precise details like we would like. And so this is where we train a model that takes the satellite imagery and predicts a distribution over these object histograms. And what we get from this is the ability to say, for any given geographic location, we can get the satellite image, and then we can predict the likely distribution of objects in a scene captured in that location. And so here are some examples of this from the San Francisco Bay Area, where if you remember the distribution over boats that we showed before, it was very coarse. You could kind of roughly see where things were, but in this example, we can see very precisely wherever this is dark green, these are areas that are, you're very likely to see boats if you take a picture in those locations. And so it highlights, essentially where our navigable waterways would be one way to look at this. And you can see, if you look at distributions over cars, distributions over trains, you can see all of these different things that you would expect to see. And this is achieved without any manually labeled training data for this task, and very precise, fine-grained, spatially appearance maps. And just to highlight this, so one of the interesting things that we can do is look at the maximal activation images. So these are, essentially what we did is took all of the images from the San Francisco Bay Area, ran them through the model, and for the given class, looked at what's the expected number of images, for example, of the class boat. This is the location in the San Francisco Bay Area that gave us the maximum expectation for the number of boats in a picture. And it's not surprising, it's a marina. And similarly for trains, for surfboards, for all of these different classes, it actually ends up discovering, something that makes sense, right? That, if you're at a sporting event here, you're likely to take a picture with a large number of people in it. And so it's, to me, it's kind of exciting that, we're able to learn these details and very fine-grained models without, collecting any additional training data. And these are only going to improve as we get additional and improved models for image understanding. And the final example that I wanted to show was, we've been, working on this problem for a while. And one of the things that we tried to do over the last year is extend this to dynamic models. So instead of just depending on location, we'd like it also to depend on location and time. Right? And so this was a paper at CVPR this year that introduced a data set we've been calling cross-view time. Essentially, we have a bunch of cell phone images and outdoor webcam images from the AMOS data set that we have known locations and we have known timestamps. And so then we can use these as samples of visual appearance and relate those to location and time. And for each of these ground level images, we also get a satellite image. And so the picture of this is actually quite similar to the first one that I showed, where we were mapping scene categories. Right now, we just have this big box. I'm hiding that just so we can look at the larger scale picture of this. But we have a big box that represents some trainable neural network. And then we have a ground level image with some image metadata. So this is the location and time of that image. And we're going to take off-the-shelf networks for transient attribute estimation and for scene category estimation. And then we're going to use those to train our neural network. So the transient attributes are just, this is from a 2014 paper. These are things like dirty, daylight, and night. These were 40 different attributes that were manually annotated by people. But now they capture a wide variety of aspects of transient visual appearance. And then scene categories, this is just the places scene categories. And so then we have a neural network here at the left that we sort of broke down into a collection of different pieces. We have the first piece here that extracts features from the satellite imagery. And what this is essentially doing is allowing us to capture very high spatial resolution features. While it may not seem like it, it turns out to be really hard to directly map location and time to visual appearance, because that is basically trying to memorize where every road, every building, every fine-grained detail of the world is, and that's just hard to do inside of a neural network. So we introduce this sort of, we think of this as like a non-parametric component where we use the satellite imagery and we extract features from that. So we extract features from the satellite imagery. We then also have smaller neural networks that take the image capture time and location and predict some features. And these are used to capture low resolution global trends. So it's hard from the satellite imagery, for example, to know if, exactly what latitude you're at or, what country you're in. So that can be hard. And so these these neural networks that use the metadata allow you to capture those trends quite easily. And so then what we have in the end is this thing that's all put together. We've got features coming in from the satellite image, from the metadata, all combined to predict these distributions over the features that we extract from the satellite imagery or from the ground level imagery. And in the end, what this is a dynamic map of visual appearance. We can essentially give it a location and a time, grab a satellite image, and then it will predict a distribution over these visual features. So we can do things like this with this, where we essentially look at slices of what the model has learned. And so here for different attributes, so the lush attribute, the warm attribute, and the gloomy attribute, we can see at different times of year. So in January, it's gloomy in the Pacific Northwest. So the brighter yellow corresponds to more gloomy and the more blue corresponds to less gloomy. So if it's January and you're in the United States, you might prefer to be in southern Texas or in southern Florida. But as the year progresses, July is less gloomy throughout the United States. And this is all just based on those visual attributes that we extracted. And you can see various distributions that capture what you might expect. For example, in the desert Southwest, west of the United States, it's much less lush in July. We can also look at slices at a given location, right? So for a given location, for one of the attributes, we can sample this for a given month. Right? So here we have the warm attribute, and the pink corresponds to the month of January, and the blue corresponds to the month of July. And then the x-axis here corresponds to the time of day, right? And so we can see that it's hard to tell whether it's warm or cold at night. But during the daytime, it's very clear that July looks warm at this location. And similarly for the cold attribute. And so that's kind of a cool thing that we have this model now that we can look at various slices of. And the question then becomes, what are applications that we could use such a model to address? And so we've, in this paper, we looked at image localization. But I thought I'd focus on this particular application, which we've been exploring further, that I think is fairly interesting. And so it's the idea of verifying image metadata, and it's particularly the timestamp metadata. And so basically the way this works is we get an image, it has a location and a time. We grab the satellite image of that location, we extract transient attribute features and scene category features from our ground level image, and then we predict the distribution over those features for the location and time that we expect. And so then what that gives us is the ability to score any given time of day and month of the year with how likely it is that an image with those visual attributes would have been taken at that particular time. And so we can make maps of this over day of the year and month or hour of the day, where dark green corresponds to it's more likely that this picture was taken in that setting at that time. And so in this case, the X marks the correct ground truth, and the darker green is where those are likely to have been taken. So you can see it rules out quite a few possible timestamps, and it focuses in on timestamps close to the ground truth. So we've got a large number of experiments in that paper, and there's certainly more work to be done sort of pushing on exactly solving this problem, but it sort of highlights one of the potential applications for a model that does essentially appearance mapping. It tells you for a given location, for a given time, what do we expect it to look like at this place? And in source, we just looked at scene categories and transient attributes, but you could easily throw in different attributes to such a model. Okay, so just sort of as a recap, and maybe to help kick off the questioning session, we've been looking at this relationship for quite a while between localization, calibration, appearance mapping, and image understanding, and how each of these, any pair of these can be useful to help build a system to do the other. And so we showed a few examples of doing that for appearance mapping. But these then, once we have this appearance map, we can turn around and use that for localization and more general calibration tasks. And with that, I'd like to thank the students that contributed significantly to this work, and for the funding under the National Science Foundation in particular that was a big part of making this a possibility. So with that, I guess I'll open it up for questions.
Thank you very much, Nathan, for the great talk. Yeah, we have time for questions. So for the audience members, you can ask questions through the Q&A box that Zoom provides. For the panelists, if you have a question, feel free to just unmute yourself and ask. And maybe I start things off. So you had this nice slide where you showed the maximum activated image for different categories, such as surfboard. Mm-hmm. And for surfboard, unsurprisingly, it gave you a beach, but it also gave you a beach with a nice surf in the sense of nice waves. Do you know whether you would still get that image with the water would be still?
Yeah, so these images, and in this particular model, the satellite imagery was, it's not connected to the time that the image was actually taken. So this imagery is, often called base map imagery. It's just intended to be useful for people that are, navigating, and it's supposed to be clean. So the particular time doesn't matter. And so I think what the model is learning is more, this looks like a beach where people might hang out, right? So there's enough space, maybe the parking lot there was part of it, that it's clearly, close to a place where it's easy for people to access. And I think it's probably learning to be invariant to the surf conditions, because that's just not part of the thing we're forcing it to learn.
Thanks. I was just wondering whether this is something that I would actually pick up on, but yeah.
So I think, I guess sort of following up on that, the other work on dynamic mapping, we wrestled with this idea for a while of whether we wanted to include images, satellite images with timestamps. And I think that that's a natural next step. There are satellite image providers that capture imagery very frequently. And so, we could start using images captured on a daily basis, as the input and match those up with the ground level image. And so then I think we would start learning to extract these sort of time varying attributes from the satellite imagery, but we included the time and location as inputs to the network to try to capture some of that time varying aspect. And in that model, the satellite imagery is only serving to capture spatial details, and these sort of smaller networks here give you the time varying aspects.
Thanks. As a follow-up, so you go from ground level imagery to satellite imagery. The advantage of satellite imagery is that you can quickly cover like huge regions. Mm-hmm. How much more complex does the problem become if you want to go from satellite to ground level?
So in terms of learning to, I guess I didn't quite get the question. So maybe can you repeat that? I feel like I didn't quite get the subtlety of that question.
Yeah, I think what I'm wondering is, so you need the ground level images to provide visual appearance, right? And you use this to reason on the level of satellite images. How complex would it be to go the other way around? So assuming you have labels for satellite images,
I see,
and you want to map it to the ground.
Yeah, so going that way is not something that we've really focused on, because there are these existing networks to do ground level image extraction, and there's a huge industry pushing that to and academia improving that. I think what you start running into are issues with the geometric registration between the two views. And so we have looked at trying to do things like, to figure out the geometrical relationship between the two so that we can then map specific things in the ground level imagery to specific things in the satellite imagery. But I think that going that way is probably of less value, just because we already have really strong data sets for learning to extract ground level image visual attributes.
Okay, thanks. Are there any questions from the audience? So if you have questions, please use the Q&A box and I'll relay them. And while you think of questions, I have maybe one more question, which is what happens in the areas that are more sparsely covered by images? So images are not taken uniformly distributed over the US, but some regions are much denser sampled, some regions are more sparsely sampled. Do you know what does the network go? What do you learn in those regions, so to speak?
Yeah, so part of the motivation for this work was to address, there was a lot of early work on image-driven mapping, so just using social media to make maps. And that has a huge problem with oversampling near tourist landmarks and high population density areas. And so this, to some extent, is a step toward trying to overcome that because the satellite imagery is available widely. Now, I think you still do have bias because you're oversampling the ground level images. And so I think you might deal with that by, just adjusting weights and things like that. We haven't really pushed onto that, but I do think that there's certainly a bias because because of the source of the ground level imagery. But I think it's less so than if we just try to use the ground level imagery directly.
Yeah, thanks. So last chance for the audience to ask questions. Don't be shy. This is fully virtual. Nothing will happen to you. Okay, I don't see any questions. So thank you very much for the great talk. Very much enjoyed it.
Okay, yeah, thanks for all the attention, and I'm looking forward to the next talks.
Okay.